do that. You put phi equal to 0.1, then find the stream function, the derivative of stream function, second derivative of the stream function, and then the first derivative of the stream function, then the stream function, you got it. You do that until you found this. You know, when you found 5, you found is 0.99. So this, you take this one, right? At that time, this thing is, for me, is incredibly precise because you got 0.99154. Okay, even you guys now, if I give you a quiz, you will not go into that. You go there. Okay, so maybe the second quiz we should try. You solve the equation without using calculator. Lausius can do this. Why you can't do it? Okay, so but if you want to get 0.9999, you need to reduce it, and then you get 4.91. Give you 0.99. It's not there. Okay, so now you can see here that F double apostrophe is proportional to the shear stress. This is the function that we have before, stream function. F is this. This function. Function of phi. This one. You take derivative of this, you get the shear stress. Sorry, you get your U. Right? You take the derivative of it, you get your U, which is the velocity component in the x direction. If you take the second derivative, you know, when you have U, you take the derivative du dy, it will give you the shear stress. So that's the reason behind it. So you get that. Okay? And the F itself is the stream function. Okay? So thankfully, Lausius has done this for you, so you don't have to do it on your own. Right? So what you need to remember is that for laminar, delta will be 4.91x over Reynolds number x. Is that complicated enough for you? Okay, but unfortunately it is not the last one. Because this one we are talking only laminar flow, the nice flow. What happens if you are dealing with the turbulent flow? For the turbulent flow, right, unfortunately there is no analytical solution. So what we obtain at the moment is empirical correlation. What is the difference between empirical and analytical? Usually, analytical, you get it from the first principle. You know, the first principle is conservation of mass. That mass cannot be destroyed or created. First principle. Second principle, energy cannot be destroyed. Yeah, that one is conservation of mass and conservation of energy. There is also conservation of momentum, conservation of ion, conservation of species, and loss. Right? That's it. So you have, if you have that principle and you derive from that, you get your analytical solution, which is exact. But when you do experiment, you have done your lab, right? Not yet. Okay, when you do your lab, you take a measurement, right? From measurement, from your lab, you'll get your measurement. This RPM, this is your power, right? You got this one, that one, this one, this one, and this one, right? You connect. Then you found out that y is equal to x squared plus bx. This one called empirical correlation. But if you derive from right, you cancel, then suddenly you got this. This one is the exact solution. Okay. This one is empirical correlation. And for the boundary layer equation for turbulence, there is no exact solution. We need to use empirical correlation, and out there is 100 or even 1,000 empirical correlation has been proposed. If you want to open a journal paper, there is a lot, but the most widely used is this 1/7 power law. So it says that U over U, but this one is your U, any U. This one is the big U, is some value, right? Usually some value is equal to that. For which the boundary condition is, the boundary layer thickness become 0.388 Reynolds number 1/5 power of 1/2. So to make our life easier, I have put the boundary layer correlation in a nice table. Okay, so you don't have to derive it from the beginning. You have to thank Blasius. Oh, I forget to change that one, not 5. Huh? The correct answer is 4.91. Okay, so for laminar, you get your delta is 4.91. And you remember the second derivation of those Fa is nothing but your shear stress. So how do you get your shear stress for this kind of thing? Is you take the second derivative of that. So all shear stress is given by that. Okay, so the friction coefficient is something that you can get it later on, right? Your shear force is nothing but shear stress times area, and the shear stress is Cf times the dynamic. What do you call it? These things? Dynamic, viscosity. This one is how come you come to my class? Mechanics 1, right? This one is dynamic pressure. So your shear stress is your shear friction, shear coefficient times the dynamic pressure. Okay. So this is always create confusion to my student because I split it into two. But in most of my calculation, I'm not using it. I'm not using this one. The reason why I don't use this one is because of this. This log, sometimes in some of your calculator, this log without anything is log with the base of 10. In some calculator, this log is natural logarithmic because there is no 10 there. So I do not want to create that confusion. Usually I will not use this one. In real life, you need to use this. In my class, you use that. Here. Doesn't mean that if you use this one is wrong. If you want to use this one, it's up to you. But in my calculation, I will use that one. Okay. Now you remember I give you example of a canoe. No. Okay, in that problem example, do you have a fully turbulent or you have a mixing? Sure. Fully turbulent in that case, because when you take 10% also it is fully turbulent, right? So in that case, if I ask you what is the boundary layer thickness, at some point you can calculate it, right? Using that. Let's say I ask you to calculate the boundary layer in the middle of the canoe, which means 3 meters. So you calculate Reynolds number at 3 meters from the leading edge. You got your REX, your Reynolds number at that position. Then you can calculate your delta, the boundary layer thickness at that point. Okay? I can also ask you what is the shear stress working on that point. If I ask you the shear stress working on that point, you need to calculate the local friction. But if I ask you what is the power needed to propel the canoe, how much forces do the kayakers need to drive the canoe? How do you calculate it? Your force is given, right? You get your shear force. You get the area of the canoe, right? The canoe is 6 meters by some width. You got it. Tau W from here. If you are talking about the total force, you need to use the so-called average friction. Okay, so if I ask you about the force without pointing at which point, mean it is the overall force. Okay, but if I ask you what is the boundary layer at that particular point, you know the Reynolds number will be Reynolds number at that point, local Reynolds number. So you need to differentiate between Reynolds number at specific point and Reynolds number average. Okay, so average is L, point is X.